Hello and welcome to this pre-recorded talk about ruin probabilities and a Markovian short noise environment. This is based on a joint work with me and my supervisor, Stefan Thonhauser. At the beginning, a short outline. We will start with the specification of the model we are interested in. Then we will talk about change of measure techniques and our renewal times. And then we'll finally summarize the results we are given. So let's start into the model. What is a Markovian short noise model? A Markovian short noise process is a process of the following form. We have some starting value lambda 0, and at random times governed by a Poisson process, we get shock events which increase our process, and in between we have an exponential decay which reduces the process. And we are looking at the Cox process with short noise intensity lambda and define our surplus process the following way. We have some starting capital U, we have some constant premium rate, and then at random times we get claims as natural, and these claims are governed by this Cox process. And the main question arising is, how does the ruin probability behave asymptotically? Here is a path of these two processes combined. Here we have the short noise process in gray and yellow. And as we can see, we have here shock events, and in between we have some exponential decay. And here we have a surplus process, a linear growth, and here we have claim times which occur and reduce our surplus. And finally, here we get ruin. Our main tool to derive the asymptotic behavior is the following equation. This was derived by Schmidli already 20 years ago, almost 30. And it states the following. If we have a function set of u which satisfies this equation, then set of u exists, is unique, and the asymptotic behavior is given since its limit exists and is finite. This is great. This is what we're gonna use, and we will bring our ruin probability in such a form. And it's quite easy if you simply condition on the first claim time, but then problems occur in our case. At first, the ruin probability depends on lambda 0, so on the starting intensity. So we cannot simply use the first jumping time, and suitable choices of the distribution are defective. This occurs very natural. This is very often the case, and we're gonna solve this by change of measure techniques. So let's talk about change of measure techniques. We wanna change the measure so our distribution B is no longer defective. And to do so, we need a multiplier. That's obvious. For this, we define two functions, alpha and theta, the following way, where m of u is the moment generating function of the claims at the point r, and my is the moment generating function of y, of the shocks of the short noise in the point minus alpha r. And we assume that this is finite and well defined. And we assume further that this expectation is finite, and then we can define the following function depending on the parameter r. It is an exponential function, which is great because exponential change of measures are always a good idea. And this function on x and lambda is an expectation 1 martingale, and we can use this to define a family of measures qr. One question arising here is, which is the best measure to use? And for this, we define the adjustment coefficient. Again, as in the Kramer-Lundberg model, we have a convex function theta, and we want a positive root of this function and choose this as an adjustment coefficient. And we assume that the measure under this coefficient is well defined. And then under this measure, ruin occurs almost surely, and we can use this to get for free somehow that the ruin probability is bounded by some exponential decaying function. This is a typical plot of such a function theta. As we can see here, it has one root and 0, and in this case, a second root 0.4, and this would be our adjustment coefficient. This would be the right choice. Now we want to talk about the renewal times. What are suitable times? As before mentioned, we need somehow the property that our lambda is always on the same point. We need that lambda is always on the same level, lambda 0. And as a second property, we want a ladder time property so that our surplus process gets less and less. And if there are infinitely many recurrence times Si of lambda, then we can define such renewal times. And under QR, there are almost surely infinitely many of them. They are almost surely finite. So we can use them under QR to define our renewal equation. The question is, what are suitable choices of the functions in this equation? We choose B, the distribution, as the distribution of the undershoot in this first time, given somehow and that this time is finite. So as you can see here, the P, this is a defective distribution. Then we choose P of U and Z of U the following way. It's somehow excluding the case that ruin occurred already before. And yeah, as mentioned, P is defective, but we can change to the measure QR where P is no longer defective. And that's what we're gonna do. And we derive the following equation. Through to the change of measure, we get this additional term here, which is somehow natural. This occurs in every model I know. And we can state the following equation, that the ruin probability times this function behaves this way. And the functions appearing here satisfy the needed assumptions that guarantee the convergence of this. So we know that our ruin probability behaves asymptotically as a constant times e to the power minus RU. So very, very similar as in many other models too. Okay, the question is, how good is this approximation? And as we see here, of course, for small u, this approximation is not quite good. Here we have the ruin probability and the confidence interval. And here we have this approximation. And as we can see here, this example, this does not fit quite well because, yeah, u is too small. If we increase the starting capital, the fit gets definitely better. So as we can see here, we hit almost exactly the ruin probability and are inside the confidence interval. So that's really, really great. So let's summarize what we have talked about. We exploit change of measure techniques via PDMP theory and get under mild conditions that the ruin probability is bounded by some exponentially decaying function. And under additional assumptions, we can exploit a renewal equation and get, in this case, that the ruin probability behaves asymptotically as a constant times e to the power minus RU. Thank you for your attention.